on today's lab, page 58, that synonym I gave you for electron domains, steric number, let me draw these. Some of these, the idea of steric number doesn't make sense based on the way it's asked. This page where you've got H2, L2, O2, H2, Cl2 would be this. O2, into a triple bond. I guess I kind of want you to skip it for that, skip the question, but I'll show you why it's insensible for those. So if I ask you how many electron domains are around this chlorine, what would you say?
One.
For this chlorine, you've got 1, 2, 3, 4. So I guess you could answer that one and say the steric number is 4 because it doesn't matter which one you're talking about. Both of them have 4. If I pointed at this hydrogen, it would only have 1, so would this one, so I guess you could answer it, but those don't have central atoms, and that's why it's weird. How many around either one of these oxygens?
3.
Yep, 3. That's 1, 2, 3. So I guess that's 3. How about for a nitrogen?
2.
2, yep. 1, 2. So that has 2. But this is why it's weird. It's not telling you which atom to point to. This one, it's either 1, H or H. This one is Cl or Cl. Down here, H is 1 and Cl is 4. Here, H is 1, H is 1, and this oxygen is 4. But these really only make sense if you have a central atom, or at least tells you which atom to pay attention to. So that whole page 58, just, I guess you can use those numbers for the steric numbers. 1, 2, 3, 4, 5, 6. Yeah. And what else to say? Okay, one more thing to say about these. If you'll go back to this one that was just for practice. Electron domains. So there's this question. Let me throw CCl4 back up here. To go back to so when we talk about hybridized orbitals, so this is those orbitals we've talked about before for electronic configurations. 5, and there's one more 1 here. So 1s, 2s, 2p, s, Hybridized orbitals. So these are atomic orbitals that we were drawing before. They're for the neutral atom. When when bonding takes place, you have, so let's do, what should we compare? Well, I'll start with, let's not start with that. Let's do, let's see. Do so electron domains, 2 things around it, 3 things around it, 4 things around it, 5 things around it, 6 things around it. So those are the ones we covered earlier today. So if you have 2 things around it, I'll say like that. So for oxygen, there's still 2 pairs like that. When there's 2 things around it, what actually happens is we'll just focus here on the S and the P. And once you get up here, you have S, P, and D, the 3D. When you have 2 things bonded, what that means is, here's what I'm doing. I'm taking those 4 orbitals and I'm sort of mixing them together, and I'll get, I shouldn't do that first. I'm going to take, we call that 2S, 2P, and forget the 1S. I'm going to take the S and one of the P's and mix them together so I have 2 equal orbitals now. I take one of the S's and one of the P's and I mix them together. 2 orbitals go in, I mix them together, I get 2 more orbitals out. And those 2 P's are still there. So, and for hydrogen, so 1 hydrogen, 1S. So this is one of the hydrogens, this is the other hydrogen. And here I've got so for oxygen, 1, 2, 6. 1, 2, 3, 4, 5, 6. One of the hydrogens, another one of the hydrogens. What I'm going to do is take those 2 so when bonding happens, there's always this hybridization that occurs. When it's 2 things around it, I'm going to take that, 1, 2, 3, 4, 5, 6. So the pairing is occurring. Maybe I should do 4 things. Yes, you do 4. Let me go back to 2, 3, 2. Let's do carbon. I'm all screwed up now. Carbon, and let's just do hydrogen. Okay, there's one where there's 4 things around it. I'll do that first, okay. So I have 4 hydrogens, and every one of those hydrogens just has that 1 electron. It wants to pair. All right, so I'm going to take all 4 of those and make them equivalent. That's called hybridization. I take the S and the 3 P's, and what I make is sp3. All right. And those 4 electrons, now, so it's sort of like, I take those 4 electrons, I set them aside, I mix the orbitals so they're the same, so I get 4 orbitals, I mix 4 orbitals together, I get 4 orbitals out, and we call them sp3 hybridized orbitals because each one of these is made up of part of an S and part of 3 P's. So the sp3 orbitals, all 4 of those hybridize become like this, and if I put those 4 valence electrons back in, has to be paired. Oh yeah, there's 4 hydrogens, right? So I have 4 like this, and I have these 4 orbitals. Let me just say this in a more simple way. If that central atom has 2 electron domains in it, that means sp hybridized. That means those 2 have hybridized to do the bonding. If there's 3 around it, it's sp2. I'm butchering this. It's sp2. And those have hybridized into 3 sp2 hybridized orbitals, with that p orbital still left over up there. And then if 4 things, sp3 hybridized. So if all of those hybridized, then we have no p orbitals left. And then if there are 5 things around it, we have to at least be up here. Do you remember how I said once you get to this level, you can have more than 4 things around it? That is, you can expand the octet. You can have more than 4 pairs around it. It manages to do that because then you can get like that, and you have sp3d orbitals hybridizing. This might not make sense. Do that, and you still have 4 d orbitals up there. This might not make sense without going into with 6 sp3 d2. So if you can take the S, 3 P's, and 2 of the D's, that's how you manage to bond to 6 different things. And you can have pairs of electrons in there. I'm butchering this. Two hybridized. try one more time. If I can't make this smooth, I'll do it Tuesday. 1s, 2s. So for beryllium, there's my valence. It's 2p, 2p. Bonding with two things. So that's what I'm showing there. BeCl2 is here. For it to bond, I'm going to take these two orbitals, they mix together, and they come back out as 2p, or as sp hybridized orbitals. Or let's say I take the two electrons, I set them aside, I hybridize those two, and I'm left with sp, 2p, and 2p. Or let's just leave the number on. So two orbitals go in, two orbitals come out as sp hybridized orbitals. Now I'll take those two electrons and put them back in. I guess I can do Cl. So if you look at Cl, how many domains are around it? 4. So if I do 4 for Cl, okay. If it's 4 around it, then I'm hybridizing all of them. So Cl hybridizes as, I'm going to take the 7 electrons out, and then these all come together as sp3. So 4 orbitals mixed together, I end up with 4 new orbitals, and here's my 7 electrons. All right. And there's 2 Cl, so let me do another Cl. So what we get when bonding happens is I have this one pairing with one of these, and then this other one pairing with another one of these. So that's the only 2 electrons that came from beryllium. And then they're pairing with these, and what you get is, yeah, I have to start drawing orbitals for this to really click. The simple thing is, if without understanding at all what hybridization is, which is why I'm trying to sneak back in the back door doing this, what we did earlier today, it's really this simple. If it's 2 things, if it's 2 electron domains, it's sp hybridized without explaining to you all what that means. If it's 3 things, think of it like this. This 2 means 2p. There's your 3 things. sp3, this is 4 things, sp, p, and p, 4 things. This is just how we notate it now. And there is a hybridization that occurs, but I better wait and look at our book and decide how we're going to use it. This, that's how you get 5 things. And then this is 6, s, p, p, and 2 ds. Hybridized to make this. And of course, this is just S and P. So we call this, making this simple. How many things do you see around beryllium?
2.
2. That means that beryllium is sp hybridized. And I know I haven't explained what that means yet. Chlorine, there is still a shape sort of around chlorine. It has four things around it. You can think of it as tetrahedral. But if it's got four things around it, it's sp3 hybridized. This is simple. Look at boron here. What's the hybridization for boron? Based on this?
SPPP.
Yes, sp3, because it's got four things around it. And same with fluorine, it's got four things around it too. Electron domains over there. This phosphorus, what's its hybridization scheme?
SP3D.
Yes, sp3d, because there's five things. I know I haven't explained to you what this hybridization is, but I think I have to start from scratch Thursday. Six things around it.
SP3D2.
sp3d2, okay. Should I try? Maybe I should try. I just gotta find where I want to do this from. Yeah, I want to wait. I'm going to end up wasting all this time today. But yeah, let me wait. All right. So let's look at this lab, just so we do something useful. I need to open. Do you have laptops so we can graph this? So, let's see what we got. Alexa's lab here. So procedure, page 50. So it's this page. You have data on this page that you filled in. So this, just above here, because of the way we had those yardsticks set up, your central maximum is just 0, and it's that you would use to correct this measurement. But since it's 0, your measurement is just your measurement. And you should have at least 3 significant figures there. I see on his 37, but you should use 37.0 if it was exactly there. So what do y'all have for, like for next to dark red for the measurement centimeters? Tell me what you've got.
I put 100 centimeters for all. Or are you talking about the correct measurement?
For this.
100, I put 100 centimeters for all.
That 100 centimeters would have been this, which I thought was 99.5 or something. Did you have a partner?
Yeah.
Did your partner do the same thing?
Yeah.
Anybody else?
38.9.
Okay, 38.9. Anybody else?
40.
40. Okay. You should get somebody else's data.
Okay. Because I put I have 38 for my corrected measurement because I thought measurement was.
Oh, okay. Just use that. If
Well,
you
that
if you
correction-
actually read those out,
Yeah.
then yeah. But that's
I thought
what
100
would have been
centimeters
here, and then that's the corrected one. But those were set up such the center was at 0 anyway. Okay. Do you know how to calculate this? So that is 37. So he has 37 here, and I guess here, and then 100 here. Did somebody have something besides 100 there? I thought those were 99.5. Maybe just one of them was 99.5. Do y'all have 100 there?
Yeah.
Okay, 100. So this is, you put 37 over 100, and then you have to do inverse tangent on a calculator. So 37 over 100, and then inverse tangent gives you the angle that's right next to it. What do y'all have for those angles?
For the angle, I have 20.8, and then for the tangent itself, I just have 0.38.
Okay. All right, so if we had, going across there, um, 37, but it should be 37.0. Corrected would be 37.0. And then he had 37, 100. And then you find sine of that angle. I guess he did that right. So what do y'all have for sine of your first one? Like his was 20.3. And then I've got to take the sine. Sine of angle, the angle, and are we all in the same ballpark there? All right. Okay, so what you do is you take the wavelength on the left and then the sine of that angle all the way over on the right, and you graph them. So I've got on the left here, this is the wavelength. Here. Sine of theta. Any of you get this far?
No.
Okay. And I graphed them. So the dark dots here, the graph, it should be generally linear, but it won't be perfect because it's experimental data. You guys with me? And then you add the trend line, and you get your equation and your r squared value. And that's what goes down here, where it says slope. So the slope here, this says 5 times 10 to the negative 5. It really should be 5.00. Excel just does this. Doesn't always know what to use for significant figures. But this one's slope is 5 times 10 to the negative 5. And then his y-intercept is this, 0.0038. So if you extrapolated this line all the way down here, that's where it would hit the edge. You're going to use that on this next page. This next page is Did I open that? I guess I didn't.
No, me too.
This page. So again, you've got your measurement, tan, the angle, the sine of the angle, and then this you're going to get from, so for his curve, let me write it down. 5 times 10 to the negative 5. X plus 0.0038. 0038. That equals the wavelength. So sine of the angle, and then what you'll do is take sine of the angle, it's this equation. So the x value you have on your graph is sine theta. So you find sine theta, you plug it in for x, you multiply through for y, and that tells you what that lambda is. So for instance, his he has for sine theta. So I'll plug that in for x, multiply this. -5 times 0.330. And I think you have to add this. So he has, and those were in angstroms. We're going to end up in angstroms. These wavelengths that are given are in angstroms. So we're going to end up in angstroms, which is 10 to the negative 10. So 5. Um, 1, 2, 3, 4, 5. Maybe we, yeah, I guess we do add that. So. Zero. It's 10 to the negative 5, 2, 3. I don't know. Because it's experimental error, but it doesn't go to 0. That makes sense to me. Any of you guys graphing this as we go?
Slowly.
I'm curious what you get for, you've got y equals mx plus b. I'm curious what you get for b, because that seems too high to be adding it. Anybody else get it graphed? You want me to help you graph it? What are you gonna do? Who's following along?
I was following along, but like I couldn't keep up fast. I was just paying attention. So now I'm actually doing it.
All right. You guys know what I mean by graphing it? You guys able to do this? Zero, zero, 3, 8. I'm curious what y'all get for an equation too. Anybody else graph this? I want to wait to see what y'all get for this.
How do you add an equation?
Hmm?
How do you you add the equations for graph?
You click on the dots so they highlight, and then you right click, you go down to add trend line. Here. All right. If you've got, delete that.
You just did a line graph, right?
Yeah. So if you get these side by side and you put wavelength on the left,
Or scatter?
yeah, and use a scatter plot. You guys with me?
Yeah.
And then you go up to insert, scatter plot, and do the one without the line. You guys with me?
Mhm.
And then you click the dots, and you right click, and you go down to add trend line. And then over here you want to click display equation on chart and display R squared value.
Yeah, I got negative 0.0084 for B.
I got positive 0.0098 for B.
They're all around the same order of magnitude. Are you getting around 5 times 10 to the negative 5?
Yeah.
I guess we could calculate it both ways. Okay, that's 10 to the 4. And what are you getting for sine?
How did you calculate sine?
You just put what you get in for, you've got your angle, and then you take sine of the angle, and his is about 0.330, sine of the angle.
Oh, I did mine for the other graph, not this one yet.
You know what I'm saying? You graphed this.
So you can try and figure out the angle.
Oh. Okay.
Pretty sure it's the measurement
You got
over.
41 there, and then you want 41 over 98,
Okay,
and then you've got to do inverse tangent.
yeah, got that. And that'll give you the angle.
Yeah. You write 41 over 98 here, and then do inverse of 41 divided by 98.
Okay.
How do you? Yeah, right.
Anybody else?
Are you looking for the calculation of the? This is how I would do it to get the wavelength.
Wavelength is, yeah, and that's what I'm trying to decide. The orders of magnitude of these are all so bad that this is going to overwhelm that. And I'm wondering what we get. I got 0.0000165.
These
But if we add those,
for like slope and the line or something. Are we getting that from this?
yeah,
Okay.
it's y equals mx plus b.
So like
m is
5
5 times 10
times-
to the negative 5. I wonder if we've got a negative off somewhere. You get it figured out.
Yeah, I'm just looking now.
That video's still going. You guys got it figured out? Anybody need help? You guys got it? You got a graph? Are y'all coming up with about the same thing for this equation?
Yeah.
Y equals mx plus b. All right. Well, we're nowhere near. We're nowhere near. still think I'm doing something wrong.
Oh.
Calibration.
Is it not to the negative fifth? Is that what makes sense?
Yeah. I mean,
Does
it
one
is
negative
10,
slope make it like the?
that's a
no, I guess it's
positive,
not negative slope. Never
that's a
mind.
positive slope, so that should be positive, and it should be positive.
I think the problem is you mixed up x and y in the equation. Because isn't our wavelength
Yes,
x?
you're right. Thank you. So what we need to be solving then is we need to be resulting in lambda though, right? So wavelength is, yes, I see that. Okay, if y'all have this, do this. Move that to the right side and graph it. Did you do this correctly already?
Maybe.
You're a step ahead of me,
I
so.
did the calculations like that.
All right, did you make the graph?
I haven't changed the graph.
All right, so wavelength on the right this time. Y'all see what I did? All right, highlight that, now insert graph. And then at trend line, equation, I think that looks better. All right. So now if I plug in, I'm going to do it here. Two oh one three three x 20.665 equals this plus this. You have point. Yes. Good. Y'all see what I did now? So what he's got is, so this is my new equation. That looks good now. 20133. And his x is 0.330 and plus 20.665. And I guess we're in three significant figures, so 6660. You guys got it?
Why don't you flip it around?
This was supposed to be on the y-axis, and this was supposed to be on the x-axis. That's what I changed.
So even though it's the dependent variable, we're still throwing it on the x.
Yeah, dependent. Yeah, we're plugging in what we got from the other graph, what we got from this graph to solve for that. So we had, this was,
Oh, because we're still, okay, I understand.
yeah, that's sine, what's down here is, Well, I want to put a title there. Chart design, yeah, there it is. Axis. So this was sine theta. Horizontal axis was did it not add? Why didn't it add? Well, it didn't. Wavelength and angstroms. And then axis tile, horizontal. Now it's sine theta. All right, so now we're plugging in the sine theta from the other page. So solving for that, 6,660. All right, energy. All right. So if you want the energy, and let's see. So if we want the energy, we've got to get the energy from the wavelength. And let's do this. We've got the wavelength. We have to find the frequency, and then use the frequency to find energy. But you could do it like this. So that's the frequency, that's the wavelength, that's the speed of light. I solved this for frequency, and then this one, energy over Planck's constant, also equals frequency. And I'm just going to make those equal to each other. E over H equals C over wavelength. And we're looking for energy. So you can use that plus two constants to find energy. So let's use that. Joule seconds, and C we've been using our wavelength is in angstroms. I guess we want to change that. What was this? 10 to the 17 nanometers. All right, what did I have? I had 660, and that's times 10 to the negative 10 meters. That's what an angstrom is, 10 to the negative 10. And should we put it in? I just thought of something else. Find the energy, and then 1 over wavelength. That's what I was thinking. So we can calculate that just from the wavelength. Joule seconds. All right, so we'll calculate the energy. I'm gonna need my Bird constant anyway, so. So let's just do this in meters. Meters. So that, we want on the bottom, and on the top we want 6.626 10 to the negative 34 joule seconds times that'll give us energy. All right, it's still on, but whoever's watching this video is going to be very bored. It's hard to make quantum mechanics sound exciting. All right, so where was I? So calculating across 0.626 times 3.00 times 10 to the negative 34 times 10 to the 8 over 6660 10 to the negative 10, 10 to the negative 34 times 10 to the 8. I'm going to bring this up to the top times 10 to the 10, 10 to the negative 34, 10 to the 18. All right, this is working out. 34 minus 18.
16.
And then now I'm doing the calculator. I've got 298, 10 to the negative 16. 3. Okay. Meters. Oh, that was a frequency. So that was 1 over S. Oh, 1.
Shouldn't it be negative 19? So you move to the right. So you
2,
go
3. Yeah. But this was a wavelength in meters. Joule seconds. Oh, yeah. This was meters per second. So the seconds cancel and the meters cancel. Okay. So this was joules. I think I did that right. Think y'all can do that?
Where are you getting the value for the wavelength?
That's what I calculated using his data before I erased everything. That's what I got when I plugged in 0.330 for X, and Y I got 6660 angstroms, which is 10 to the negative 10 meters. You know what I'm saying?
Yes.
So for his data, he calculated over here at 0.33, and then that's what we plugged in for X,
Into the, got it.
and mine came out at 6660, which is what that's at. All right. And that 6660, I'm using that for the wavelength with these two constants to find the energy in joules. You guys okay? Am I leaving you in the dust? Anybody lost here? All right. The next thing, so that's what I found for energy, 2.9 times 10 to the negative 19 joules. And the next thing is to calculate this energy level. It says to assume n equals 2 as the final energy level. And we're going to use this equation. So now I have to do, so yours won't come out exactly like this. I'm just showing you how to solve for it. Because his was 6,660. All right. And his wavelength, I have that for angstroms. This constant is this, and that's in meters, 1/meters. So I've got to put that back to meters, so. It's 10 to the negative 10 meters equals 0.96776. 10 to the 7, 1/meters. All right, and then and this right here, when it says calculate the energy level, it's got an arrow pointing to a 2. It's saying so initial, final. So I'm going to put in here for my final, I'm going to go ahead and put 2. So that's telling you the photon that was responsible for that wavelength of energy came down from some higher level, n equals something, that's supposed to be a question mark, some n down to n equals 2. So it's telling us to assume it landed at n equals 2. That's what this is telling us. N arrow to 2.
So we're not using the equation of before. We're using this one. Or we're using both.
Yeah, where's equation 4? Do they tell you to use equation 4?
Yeah, I'm back here. It's just a little bit different. The
Well, let me
constant's
look
different.
at it. It's on the back.
It's on the page 46, so somewhere in the front.
$2,178 times 10 to the negative 18 joules. You could do it either way, actually.
So even though the 2.178 and the 1.096 are two different numbers,
Yeah. 178. They're using, I wonder if they have that in this book. So they're
Oh, because you
doing
also
this.
put wavelength in this.
Yeah, it's related to this, but I'm doing it off the wavelength. You could use that equation too.
Okay.
I guess I could do it both ways to make sure. But we're gonna go through a bunch of math here and then try to solve for that integer. Crap, what did I get for energy? I didn't write it down. Did you write it down, Lex?
It's well, you had 2.98.
Yeah.
10 to the negative
10 to the negative 19 joules. All right. So if I use that equation, delta E, that's joules, okay. Two squared minus 1 over n squared. So maybe I should solve it this way. That looks way more simple. Okay. Yes. Equals. All right. So we'll use that equation. That looks way more simple. 2.98, 2.178, 10 to the negative 19 times 10 to the 18. All right. 1 over 2 squared, 1 over n squared. All right, let's do a little bit here. 2.98 divided by 2.178. I got 1.37 times 10 to the negative 1 equals 1 over 4. 2 times 2. All right. Is that 1.37? 2.98 divided by 2.178. Yeah, 1.37. Now let's go ahead and do this times 10 to the negative 1. Equals. Right. All right, 1 over 4 is 0.25. So I'm going to subtract that from both sides. So that's 0.25, 0.25 equals negative 1 over n squared. 0.137 minus 0.25, negative 0.113 equals negative 1 over n squared. All right, and let's just take the negative off. Go ahead and multiply both sides by negative 1. I want to take the inverse of both sides, so I'm going to do 1 over follow me there. So take the inverse of both sides. Does that make sense? You guys okay? 1 divided by 0.113. I got 8.85 equals n squared. I could take the square root of 8.85. I'll just do it. Where's my square root?
So divided by negative 1.
So square root of that, I get n, and here I get 2.97. These need to be integers, but you can see what integer that rounds to. So there's still a little experimental error. We didn't land right on one of these integers. But what do you think n is for that? N's should be integers, just perfect integers.
So 3.
So it's essentially 3, so n equals 3. And yours should come out the same, doesn't it? It'll be off by a little bit, just from experimental error, but. Did I not open that? I did open that like this. So show your math. Where is it?
Page 52.
Page 52?
Yeah.
All right. Theoretical energy level transition. Okay. I guess you don't enter anything in this column, and over here, n equals 3. That very last column, you just write n equals 3. And yours should come out to n equals 3. Your math will be off just a little bit at the end, but you should round very close to a 3 there. You want me to go back through it? Just once? All right. You take, now that I've stumbled through it and y'all told me what I did wrong, you have this graph, or this set of data, page 51. You measured a certain number of centimeters. It's 37 something in the low 40s, something like that. Anybody not have that? Be honest, I'm going to help you. I'm not going to dog you. So around 37, 40, low something. Anybody not have that for these? He has 37, 34.8, 30, 25.5. All right. And then you just rewrite it here because that correction was 0. All right. And then whatever you had for this, he has 100. Somebody I saw had 98. I thought one of those was 99.5. Does anybody have something weirder than that here? So maybe it was 100 centimeters, maybe it was 95.5, maybe it was 98. All right, and this is 0. So you take this and put it over that. So in his case, he had 37 over 100. That's what he literally has written right here. You with me? You following along? All right. So you take your calculator, and I'm going to go 37 divided by 100. I got 0.37. And now I'm doing inverse tangent. On these, you hit the key that says second, and then you hit tangent. Second. Where is it? Second tangent. And it gives me 20.3. So that's what I have for my angle. So I now have 20.3 right here. And then I'm going to take the sine of that, turn off your second key, and hit sine, and that gives me 0.347.